Hello and welcome to Lecture 3 of the Interactions Unit of Phys 1104. In this lecture we're going to look at source energy, which I mentioned at the very end of the last lecture, and we're going to look at how many interactions take place on length scales that are far smaller than what we can typically observe on a day-to-day basis. To start off, let's think a little bit more about dissipation and see how it actually has to do with length scales and the internal structure of objects. So think about some rubber balls bouncing around inside a box, and for comparison, think about atoms of gas moving in a container. You can certainly picture the rubber balls bouncing in the box, and so we often picture the motion of atoms of gas in much the same way. But there's a very important difference between them. If you just wait a little while, and if you're not shaking the box around to introduce more energy into the system, the rubber balls will eventually settle down and be lying stationary in the bottom of the box. But the atoms of gas in the container just keep moving. Why? What's the difference? Well, the rubber balls, of course, are made out of atoms, and initially those atoms are moving in tandem, and so the system has a lot of coherent energy. We say that it has energy at the macroscopic scale. By macroscopic, physicists just mean length scales that we experience on a day-to-day basis and have access to with our own senses. But later on, that coherent energy on the macroscopic scale gets turned into incoherent energy on the microscopic scale in the form of all the atoms jiggling around randomly inside the balls. This is thermal energy. And so it's this transformation of coherent macroscopic scale motion into incoherent microscopic scale motion, which is really what we mean by dissipation. But in contrast to all that, the atoms of gas don't have internal structure. Atoms aren't made of atoms, and so no dissipation occurs. Now you may object, wait a second, Jeff, atoms sure do have internal structure. They're made out of electrons and protons and neutrons. Well, yes, that's true. But those things all obey quantum mechanics, and one of the things that means is that they can only take in energy in certain discrete amounts, and the amounts of energy they need to take in are larger than the typical energy of the motion of the atoms around in the container. And so it's impossible for the energy of the motion of the gas atoms in the container to be transferred into those internal types of energy that the atoms have. Now let's talk about source energy, and I'm going to contrast source energy with potential energy because there are some ways in which they're very similar, but there are some very important differences between potential energy and source energy. So let's think about two carts being pushed apart by a spring, and as long as we include the spring and both carts in the system so that all those interactions are internal, we can define a type of energy inside the system that we call the spring potential energy, and that's being converted into kinetic energy. Now let's think about, on the surface, a rather similar situation where instead of a spring we're using an exploding firecracker to push the two carts apart. Now, if we include the firecracker and the two carts in our system so that once again those are all internal interactions, we can define an internal energy in the system that we call the chemical energy, which is a kind of source energy. And notice that just as we can think of the spring potential energy as energy stored in the compression of the spring, we can think here about the chemical energy as energy stored in the unexploded chemicals in the firecracker. And again, that chemical energy gets converted into kinetic energy of the carts. But this time you know that when the firecracker explodes, and don't try this with our carts in the lab because things get hot, and so there must be some thermal energy as well. So other than that thermal energy, though, which is a big clue about something very different going on here, these two situations look rather similar. We have a stored energy, which is being converted into kinetic energy. But you can really see the difference if you think about something different. If you reverse the interaction, you can reverse the interaction with the two carts and the spring. You can have the carts move towards each other and compress the spring and convert kinetic energy back into spring potential energy. However, there is no way you can have the carts move towards each other, make the explosion go in reverse so that it says "moo back" instead of "kaboom," and have the firecracker reform. That's impossible. And so the conversion of the chemical energy into the kinetic energy of the carts is irreversible, as opposed to the reversible transformation of the spring potential energy into kinetic energy of the carts. Like potential energy, source energy can be thought of as a type of energy that's stored in objects, but unlike it, whenever we convert it to other forms, we do so irreversibly. We'll call it source energy, but there are many kinds. For example, chemical energy, which is what we just saw with the firecracker, and typical sources are coal, oil, gas, wood, any burnable fuel, but just about any chemical reaction that you can make go spontaneously will result in chemical energy in your set of chemicals being converted into other forms of energy. Another type is nuclear energy. Whenever nuclear fission or nuclear fusion or nuclear decays occur, then nuclear energy inside the nuclei of atoms is converted into other forms. Solar energy. Light can be thought of as a rather mobile storage medium for energy, and we can harvest that energy just like we harvest things like chemical energy. Because energy is extensive, we can do the same sort of accounting for it that we do for momentum, and we've seen this in earlier lectures, but now it's worth reviewing it because we have more tools at our disposal. We know all of the kinds of energy that the energy within a system can take: kinetic, potential, source energy, and thermal energy. And of course, potential energy has many types, and source energy has many types, but these four broad categories are the main categories. And so let's think about how we can transform back and forth between them. We can transform kinetic into potential energy and potential energy into kinetic energy back and forth, and this is reversible. But in any real system, eventually the kinetic energy and potential energy will get converted irreversibly into thermal energy because of friction and air drag and other similar forces. We can convert source energy into kinetic energy and potential energy, but every time we do, some of the energy gets transformed into thermal energy. We cannot transform source energy directly into kinetic energy and potential energy without some of it winding up as thermal energy. The reasons for that are rather complicated, and you'll have to take a thermodynamics course to learn more about that. What you can do, though, is convert source energy directly into thermal energy. Interactions really are the fundamental building blocks of all of physics, because in fact we define properties of matter according to what kinds of interactions the matter takes part in. For example, think about a simple question like, what makes an object a magnet? Well, if you have some object and you want to know whether it's a magnet, there are tests you carry out to find out. Does it attract and repel other magnets? Does it attract ferromagnetic materials like iron and nickel? And perhaps less obvious to you, does it interact with moving charges to make their paths curve? But notice, all of these tests are looking at what sorts of interactions the object that you think might or might not be a magnet participate in. And so it's the participation in those interactions that defines the thing as a magnet. And this goes for all sorts of other properties of matter. If you want to know whether something is charged, you look at the electrical interactions that it participates in. If you want to know whether something has mass, and this time I really do mean mass, not inertia, you look at its gravitational interaction with things. As we've seen in an earlier lecture, interactions can be long-range or contact, but in fact all interactions have some sort of interaction range. Let's start with magnets. This is a long-range interaction, and it's observable over the sorts of distances that you can see with your own senses, macroscopic distances. And if we think about the strength of that interaction between the magnets, it has some strength, which depends on the separation between the magnets. As the magnets get close together, the interaction gets stronger. and it tails off towards zero over a distance of a few tens of millimeters, perhaps. And so we could talk about a few tens of millimeters as being the typical interaction range for that magnetic interaction. Now contrast that with a cart sitting on a track. This is a contact interaction, and so as far as your eyes are concerned, the interaction strength is 0 when the wheel is not in contact with the track, and then it has some strength when the wheel is in contact with the track. But if you can look at microscopic scales, you see that in fact the wheel never quite touches the track. Its atoms hover close to the atoms of the track, interacting through an interaction with, again, a strength that varies with distance. But the interaction range is only a few tenths of a millimeter. This explains for us later on why contact interactions can have almost any strength. If you press down on the cart, you are in fact pressing the wheel closer to the track by a few tenths of a millimeter, and the interaction gains strength. So this is telling you that touching may not quite be what you think it is. Since all interactions take place at some range, even though that range may be rather short for some interactions, we need a model that we can use to talk about this. A model that we'll use a lot in Phys 1204, not very much in this course, but I'm going to mention it briefly, is the field model. So here's an example of the picture that we have in the field model. This is a charge, and it interacts with other charges in the region. In this picture, there are no other charges in the region, but these lines are representing the electric field of this positive charge. And we're thinking of the electric field as existing everywhere in space, but of course we can't draw lines everywhere, then the whole picture would be white. But the lines represent the directions that interactions would accelerate nearby charges due to their interaction with this charge. And one thing to note is that any disturbance in this field propagates out at a finite speed. So if the charge is moved, its electric field lines are disturbed and the disturbance propagates away. And so any interaction with a nearby charge would have a slight delay associated with it whenever this charge moves. I'm just going to finish this lecture by briefly mentioning the fundamental interactions, because every other interaction, all of the ones we'll look at in this course, are in fact various manifestations of these, mostly the first two. The most familiar one, of course, is gravity, and gravity acts over very long ranges, including galactic length scales, and this is therefore an infinite range interaction. Let's take its strength as 1. It'll be our reference for the other interactions. The electromagnetic interaction is also infinite ranged. Light is an aspect of electromagnetic interactions, and you can look up in the sky at night and see stars that are incredible distances away, and those are electromagnetic interactions between those distant stars and your eyes. You might be surprised that its relative strength is so much larger than gravity's. But just look at this rod, which has been charged, and with its static electric interaction, it's picking up these little pieces of paper. Well, it's having a tug of war with the whole Earth, and the tiny little charged rod is winning that tug of war because the electromagnetic interaction is so much stronger than gravity is. Just about every interaction we're concerned with when we're building bridges, building engines, doing chemistry, are in fact various manifestations of the electromagnetic interaction. The remaining two, the weak and the strong interaction, take place on nuclear length scales, and so they won't come into this course very much.